Hello there, and welcome to Sleep Science, where we explore fascinating science in a gentle, relaxing way that helps your mind unwind and drift off to sleep. Before we begin tonight's journey, feel free to share what time it is and where you're listening from. Tonight, we're going to explore one of those wonderfully impossible questions. What would happen if Earth simply stopped spinning? Not slowing down gracefully over millions of years, but just suddenly, quietly, coming to a complete halt. It's the kind of cosmic thought experiment that makes you grateful for the gentle, steady rotation that rocks us through our days and nights like the world's most reliable cradle. We'll wander through the immediate chaos and the slow, strange beauty that would follow. We'll see oceans relocate, discover new kinds of weather, and witness a planet that's half furnace, half freezer. Along the way, we'll find that our spinning world is far more delicate and remarkable than we usually pause to consider. We hope this isn't too riveting to keep you awake, but if it does, at least you'll drift off knowing why you should be quietly grateful for the ground beneath you, spinning faithfully through the cosmos. So settle in, take a slow breath, and let's imagine what happens when the world stands still. Right now, as you listen to this, you're traveling through space at about 1,040 miles per hour, and you can't feel a thing. That's the speed you're moving if you happen to be near the equator, where Earth's rotation is fastest. If you're closer to the poles, you're spinning a bit more slowly, maybe 700 or 800 miles per hour. But wherever you are, you're definitely moving, carried along by a planet that completes one full rotation every 23 hours, 56 minutes, and 4 seconds. We round it up to 24 hours for convenience, but Earth is a bit of an overachiever, always finishing just a little early. This rotation is so smooth, so consistent, that we barely notice it. There's no cosmic seatbelt warning, no turbulence, no gentle reminder from the universe that you're hurtling through space on a spinning ball of rock. That's because everything around you is moving at exactly the same speed. Your coffee mug, your cat, the air you breathe, the building you're in, everything is part of the same rotating system, like passengers on the world's most reliable merry-go-round. But this gentle spin does far more than just carry us through space. It shapes almost everything about life on Earth. Take our day and night cycle, for instance. As Earth rotates, different parts of the planet face the sun, creating the rhythm of dawn and dusk that our bodies and minds have evolved to follow. Without this rotation, there would be no such thing as a day, at least not in any way we'd recognize. The spin also creates something called the Coriolis effect, a phenomenon that sounds complicated but is actually quite elegant. As Earth rotates, anything moving across its surface, air, water, even missiles, gets gently nudged sideways. In the northern hemisphere, things curve to the right, in the southern hemisphere to the left. This invisible force helps create our weather patterns, guides ocean currents, and is the reason hurricanes spin in those beautiful, terrifying spirals. It's also why toilet water doesn't actually spiral down the drain in different directions on different sides of the equator, despite what you might have heard. That's just a charming myth. Ocean tides, too, depend on our rotation. While the moon's gravity pulls our oceans back and forth, it's Earth's spin that creates the rhythm of high and low tides. As the planet rotates beneath the moon's gravitational influence, different parts of the ocean bulge toward our celestial companion, creating the twice-daily dance of advancing and retreating waters that shapes coastlines and marine life. Even Earth's shape owes something to this spin. Our planet isn't perfectly round. It's slightly flattened at the poles and bulges at the equator, like a ball that's been gently squeezed at the top and bottom. This happens because the centrifugal force of rotation pushes everything outward, especially at the equator where the spin is fastest. The difference isn't huge, about 26 miles between the polar and equatorial diameters, but it's enough to matter for things like satellite orbits and very precise measurements. The atmosphere, too, participates in this grand rotation. All that air above your head is spinning along with the solid Earth below, held in place by gravity and friction. Without this atmospheric co-rotation, we'd experience constant, devastating winds as the air tried to keep up with the ground beneath it. Instead, we get gentle breezes, predictable weather patterns, and air that obligingly stays where we need it for breathing. Perhaps most remarkably, this rotation helps stabilize our climate. The spin distributes solar energy around the planet, preventing any one region from getting too hot or too cold for too long. Heat from the tropics gets mixed with cooler air from the poles, creating the circulation patterns that keep our planet's temperature within a range that life finds agreeable. Even our magnetic field, that invisible shield protecting us from harmful solar radiation, is generated partly by Earth's rotation. Deep in our planet's core, molten iron swirls and flows, creating electric currents that produce our magnetic field. This rotation-driven dynamo has been running for billions of years, quietly deflecting solar wind and cosmic radiation that would otherwise strip away our atmosphere and make the surface far less hospitable. So, while you sit there, perfectly still from your perspective, you're actually part of an intricate, spinning system that creates weather, seasons, tides, days, nights, and the very conditions that make life possible. It's a performance that's been running for over 4 billion years, so reliable that we've built our entire civilization around its steady rhythm. But what would happen if this ancient dance suddenly stopped? What if the curtain fell on rotation itself? Well, that's where our story takes a rather dramatic turn. Picture this. It's Tuesday afternoon, you're making tea, and somewhere deep in the cosmos, a cosmic brake pedal gets pressed. In an instant that defies all known physics, Earth's rotation comes to a complete halt. The planet stops spinning, but here's the thing, everything on it doesn't get the memo. You, your tea, your house, the atmosphere, the oceans, and every loose object on the planet's surface would continue moving eastward at whatever speed the rotation had been carrying you. And that speed, depending on where you are, could be anywhere from 700 to 140 miles per hour. To understand what this means, imagine you're in a car traveling down the highway at 60 miles per hour. Now imagine that car hits an invisible, immovable wall and stops instantly, but you keep going at 60 miles per hour. That's essentially what would happen to everything on Earth, except the speeds involved are roughly 15 times faster than highway speeds. At the equator, where the rotational speed is highest, the devastation would be almost unimaginable. Every building, tree, car, and person would become a projectile moving eastward at over 10 miles per hour. Cities would be wiped clean as if by an impossibly powerful wind, except it wouldn't be wind, it would be the buildings themselves, along with everything in them, continuing their journey through space while the ground beneath them stood still. The atmosphere itself would become a weapon. All that air, which had been peacefully rotating along with the planet, would suddenly become a hypersonic blast of gas moving faster than the speed of sound. The resulting pressure waves and winds would be unlike anything in Earth's geological record. Think of it as every hurricane that's ever existed, happening simultaneously across the entire planet. But even in this cosmic catastrophe, physics would remain beautifully consistent. The laws of motion that Newton described centuries ago would play out on a planetary scale. Objects would continue in straight lines unless acted upon by an outside force, and suddenly the ground beneath them would become that outside force, creating friction and devastation as momentum gradually transferred from moving objects to the stationary Earth. The process wouldn't last forever, though it would feel like it. Gradually, Over a period of hours or days, friction would do its work. The atmosphere would slow down as it dragged against mountains, valleys, and whatever remained of the surface. Objects would eventually come to rest, though by then the planet's face would be completely transformed. Interestingly, not everything would be affected equally. The closer you are to the poles, the slower your rotational speed, so the devastation would be less severe. Someone standing at the North or South Pole would experience almost no immediate effects, since the poles themselves barely move during Earth's rotation. It's a bit like being at the center of a merry-go-round versus sitting on the outer edge. The center barely moves while the edge whips around. Underground structures might fare better too. Deep mines, subway tunnels, and basement foundations would be somewhat protected by the surrounding Earth, though they'd still experience tremendous stresses as the ground above them tried to catch up with its new stationary status. Bodies of water would present their own unique challenges. Oceans and lakes, being fluid, would continue flowing eastward like massive tsunamis, carrying everything in their path: ships, marine life, coastal cities, along for the ride. The Pacific Ocean, stretching across a third of the planet, would become a wall of water moving at tremendous speed, reshaping coastlines and carrying its contents halfway around the world before finally settling. Perhaps most dramatically, the planet's entire surface would eventually need to accommodate its new reality. Earth's crust, which had been under constant centrifugal stress from rotation, would begin to adjust. The equatorial bulge, built up over billions of years of spinning, would start to settle. This wouldn't happen quickly. Geological processes take time, but over months and years, the planet would gradually become more spherical as it adjusted to its new, non-rotating state. In the immediate aftermath, assuming anything survived the initial chaos, the planet would be a very different place. The familiar patterns of wind and weather would be completely disrupted. Ocean currents, which depend on rotation to maintain their flow, would collapse and reform in entirely new ways. The Coriolis effect, which shapes everything from storm systems to the path of a baseball, would simply vanish. And then there would be the strange new silence. No more gentle whoosh of air moving with the planet's rotation. No more subtle sense of motion that we never consciously noticed, but which had been there all along. Earth would finally be still, truly still, perhaps for the first time in its 4.5 billion year history. Of course, none of this could actually happen. There's no known force in the universe that could suddenly stop a planet's rotation without destroying it entirely. The energy required would be so enormous that it would likely vaporize the Earth long before it could simply make it stop spinning. But in our gentle thought experiment, we can imagine the impossible and explore what follows. The immediate catastrophe would eventually end, and then the real adventure would begin, because a non-rotating Earth would be unlike anything our planet has ever experienced. It would be a world of endless day and eternal night, of new weather patterns and relocated oceans, of challenges and changes that would reshape the very definition of what it means to live on Earth. The atmosphere, it turns out, hadn't gotten the memo about stopping. While the solid Earth ground to a halt in our impossible scenario, the air above it continued rushing eastward at hundreds of miles per hour, creating winds unlike anything our planet has ever experienced. These wouldn't be ordinary storms or hurricanes. They would be a planetary-scale atmospheric catastrophe, a reorganization of the very air we breathe. To understand what would happen, let's think about how our atmosphere normally behaves. Right now, as you breathe, you're inhaling air that's rotating along with the planet at roughly the same speed as the ground beneath your feet. It's a perfect partnership, held together by gravity and friction. The air near the surface drags along the ground, while the ground, in turn, pulls the air along through friction. It's been this way for billions of years, a quiet cooperation that makes weather patterns predictable and flight possible. But suddenly, that partnership would be shattered. The atmosphere, having enormous momentum from billions of years of rotation, wouldn't stop just because the ground did. Instead, it would continue its eastward journey, creating surface winds that would make the most powerful hurricanes look like gentle breezes. At the equator, these initial winds could reach speeds of over 10 miles per hour, faster than the speed of sound. That means the air itself would create shock waves, sonic booms rippling across the landscape as the atmosphere struggled to adjust to its new reality. The sound alone would be deafening, a continuous thunder rolling around the planet. But here's where it gets interesting from a physics perspective. These extreme winds wouldn't last forever. Friction is a patient but persistent force, and it would gradually slow the moving air by transferring energy from the atmosphere to the stationary ground. Mountains, forests, buildings, anything that stuck up from the surface would act like brakes, catching the wind and slowing it down bit by bit. The process would create new kinds of weather patterns, unlike anything we've seen. Normally, Earth's rotation creates predictable wind patterns, trade winds, westerlies, and polar easterlies that form organized bands around the planet. These patterns help distribute heat from the equator to the poles and create the relatively stable weather systems we're used to. Without rotation, all of that would collapse. Instead, we'd see entirely new circulation patterns emerge. The temperature difference between the sun-facing side of our stopped Earth and the dark side would become the primary driver of atmospheric movement. Hot air would rise on the sunny side and flow toward the cold side at high altitude, while cooler air would rush along the surface back toward the warm side. It would be like a planetary-scale convection cell, a massive loop of circulating air driven by temperature differences rather than rotation. The jet streams, those fast-moving rivers of air that currently circle the planet and influence weather patterns around the globe, would completely disappear. These streams depend on the Coriolis effect, which is created by Earth's rotation. Without rotation, there would be no Coriolis effect, and without that, no jet streams. Weather systems would move and develop in completely different ways. Cloud formation would become a whole new science. Currently, clouds form in patterns influenced by rotation-driven wind systems, pressure differences created by the Coriolis effect, and the distribution of heat around our spinning planet. On a non-rotating Earth, clouds would form primarily along the boundary between the hot and cold sides, creating a perpetual band of weather activity in the twilight zone where these two extremes meet. Rain patterns would be revolutionized too. Instead of the complex seasonal patterns we're used to, precipitation would likely concentrate in specific regions where hot air from the sun side meets cold air from the dark side. These areas might experience almost constant storms as the atmosphere continuously tries to balance temperature differences. The atmospheric pressure itself would redistribute. Currently, Earth's rotation helps create the high and low pressure systems that drive our weather. Without rotation, pressure patterns would reorganize around temperature differences, creating entirely new zones of high and low pressure that would persist much longer than current weather systems. Interestingly, the upper atmosphere might actually become calmer in some ways. The complex interactions between different layers of air that create turbulence and storm systems depend partly on rotation. Without that rotational complexity, some parts of the atmosphere might settle into simpler, more stable patterns, though they would be patterns unlike anything we've ever observed. The ozone layer, our protective shield against harmful solar radiation, would also be affected. Its distribution and movement depend on atmospheric circulation patterns that are influenced by Earth's rotation. On a non-rotating planet, the ozone would redistribute according to the new circulation patterns, potentially leaving some areas more vulnerable to radiation while overprotecting others. Over time, perhaps months or years, the atmosphere would eventually settle into new, stable patterns. The initial hypersonic winds would fade as friction gradually brought airspeeds down to more manageable levels. But the final result would be weather systems completely unlike anything in Earth's current experience. Think of it as the planet learning to breathe in an entirely new way. The old patterns, developed over billions of years of rotation, would be replaced by simpler but more extreme circulation systems, driven purely by temperature differences between the planet's light and dark sides. And in this strange new atmospheric reality, any life that somehow survived the initial catastrophe would have to adapt to weather patterns that change, not with seasons or jet stream movements, but with position relative to the boundary between eternal day and endless night. It would be a world where your local weather would depend not on the time of year, but on how close you were to the line between the sun and the shadows. Water, bless its flowing heart, is terrible at following new rules quickly. When Earth stopped spinning, the planet's oceans would face the same physics problem as everything else. They'd keep moving eastward while the seafloor beneath them suddenly stood still. But water, being liquid, would handle this situation in its own uniquely dramatic way. Instead of simply tumbling like buildings or trees, the oceans would become massive walls of moving water, tsunamis that would dwarf anything in recorded history. Picture the Pacific Ocean, stretching across a third of the planet, suddenly becoming a liquid continent, traveling eastward at hundreds of miles per hour. The water wouldn't stop at coastlines. Coastlines would become temporary obstacles in the path of moving seas. Eastern shorelines around the world would face oceanic tsunamis moving faster than jet planes, carrying with them everything the seas had collected: marine life, ships, icebergs, and countless tons of sediment. The Indian Ocean would sweep across Asia. The Atlantic would surge over Europe and Africa. The Pacific would inundate the Americas. It would be a planetary reshuffling of water on a scale that makes biblical floods seem like puddle splashing. And unlike normal tsunamis, which eventually recede, these waters would have nowhere familiar to return to because the entire ocean circulation system would be in chaos. But here's where the story becomes even more interesting. Water doesn't just move, it also responds to gravity. And without Earth's rotation, gravity would begin to redistribute the oceans in an entirely new way. Currently, our planet's spin creates a centrifugal force that pushes water toward the equator. It's subtle, but it's enough to make sea level at the equator about 13 miles higher than it would be on a non-rotating planet. That's a lot of water being held in place by rotational force. Without that force, all that equatorial water would begin to flow toward the poles. Slowly, over months and years, the oceans would drain away from equatorial regions and pool at the north and south ends of the planet. The result would be a new geography unlike anything we've ever seen. Vast polar seas surrounding much smaller continents, while broad bands of former ocean floor would emerge as dry land around the equator. Imagine the mid-Atlantic ridge, normally hidden under miles of ocean, suddenly becoming a long, winding mountain range stretching from the Arctic to the Antarctic. Ocean floor that had been dark and pressure-crushed for millions of years would see sunlight for the first time. Creatures adapted to deep-sea life would find themselves stranded in air, while new rivers would form to drain the emerging continents toward the distant polar seas. The deepest parts of our current oceans, places like the Mariana Trench, might become the only spots at the equator still covered by water, forming a scattered chain of deep lakes across otherwise dry seabed. Meanwhile, the polar regions would become vast, deep oceans, potentially much deeper than anything we have today, as all that redistributed water concentrated in smaller areas. This new ocean configuration would create entirely different circulation patterns. Currently, ocean currents like the Gulf Stream are driven partly by Earth's rotation, carrying warm water from the tropics toward the poles and cold water in the opposite direction. These currents help regulate global climate and weather patterns. Without rotation, and with the oceans in completely new locations, circulation would be driven primarily by temperature differences and wind patterns. The new polar oceans would likely be quite cold, receiving little direct sunlight and having no warm equatorial currents to moderate their temperature. They might develop thick ice coverage, creating a planet where the poles are covered by frozen seas while the equator becomes a band of exposed land. Marine life would face unprecedented challenges. Creatures adapted to specific ocean depths, temperatures, and current patterns would suddenly find their world completely rearranged. Deep-sea fish accustomed to crushing pressure and eternal darkness might find themselves in shallow polar waters. Coral reefs built over millennia in warm, shallow equatorial seas would be left high and dry on the exposed ocean floor. Some marine ecosystems might actually benefit from the change. The new polar oceans could become rich feeding grounds as nutrients from the former ocean floors mix with the relocated waters. Cold, deep water is often rich in nutrients, and these new polar seas might support abundant life, though it would be life quite different from current marine ecosystems. The tides, too, would change dramatically. Currently, tides are caused by the moon's gravity pulling on our rotating Earth, creating bulges of water that move around the planet as it spins. Without rotation, tides would become much simpler, but also quite different. The moon would still pull on the oceans, but instead of creating moving tidal bulges, it would create a more static pattern where one side of each ocean is always pulled slightly toward the moon while the other side is pulled away. Coastal environments, if they existed at all in this new configuration, would be completely different. The gradual transition from land to sea that we're familiar with would be replaced by dramatic boundaries between the elevated equatorial continents and the deep polar oceans. There might be spectacular waterfalls where rivers plunge from the emerged equatorial land masses down toward the distant polar seas. The salt content of these new oceans would also change over time. As the waters redistributed, they would pick up different minerals from newly exposed seafloors and deposit others in new locations. The chemical composition of seawater, stable for millions of years, would begin to shift as the oceans literally found their new place on the planet. Eventually, after perhaps thousands of years, this aquatic chaos would settle into new, stable patterns. The oceans would find their new equilibrium, pooled at the poles and connected to the equatorial continents by whatever rivers and streams could form in the new landscape. It would be a blue planet still, but one where the blue had migrated to the ends of the world, leaving the middle dry and exposed to the sky. Half the world would wake up to a sunrise that never ends, while the other half settles into the longest night in Earth's history. This is perhaps the most profound change that would come with a stopped Earth, the end of the day-night cycle that has shaped life on our planet for billions of years. Currently, Earth's rotation gives every location its turn facing the sun, creating the rhythm of light and dark that governs everything from human sleep patterns to flower blooming cycles. But on a stationary planet, geography would become destiny. Your location would determine whether you lived in perpetual noon, eternal midnight, or somewhere in the gentle twilight between them. The sunny side of our stopped Earth would experience something no place on our planet has ever endured: endless daylight. The sun would hang motionless in the sky, neither rising nor setting, just blazing down hour after hour, day after day, year after year. But this wouldn't be the gentle, cycling warmth we're used to. Without the relief of night to cool things down, temperatures on the sunny side would begin to climb. Initially, the temperature rise would be gradual. The Earth's atmosphere and oceans have enormous capacity to absorb heat, like a giant thermal sponge, but that sponge has limits. Without the regular cooling period of night, solar energy would accumulate continuously. Regions directly facing the sun would bear the brunt of this heat buildup, potentially reaching temperatures hot enough to boil water. The air itself would become almost unbearably hot and might start to shimmer with heat mirages across vast landscapes. Meanwhile, on the dark side, the opposite would occur. With no sun to provide warmth, these regions would begin radiating their heat out into the cold of space. Earth's surface temperature, normally maintained by the daily dose of solar energy, would start to drop and keep dropping. Without the sun's warming rays, the dark side would gradually become a frozen wasteland, with temperatures potentially falling far below anything currently experienced at Earth's poles. But the most fascinating region would be the twilight zone, the band around the planet where these two extremes meet. Picture a permanent sunset or sunrise stretching around the entire circumference of Earth. This ring of eternal twilight would be the most temperate region on our stopped planet, receiving indirect sunlight, but never the full blaze of direct solar heating. This twilight zone would likely become Earth's new habitable band, assuming any life survived the initial catastrophe. Temperatures here might remain within a range that liquid water could exist, though they would vary depending on how much reflected light and heat reached different parts of the zone. Areas closer to the sunny side would be warmer, while those nearer the dark side would be cooler, creating a gradient of climates within this band. The length of this twilight zone would depend on Earth's atmosphere. Light can bend and scatter through air, creating the soft illumination we see during dawn and dusk. On our stopped Earth, this atmospheric scattering would create a buffer zone of dim but potentially usable light, extending some distance into what would otherwise be the dark side. The thickness of this zone would depend on atmospheric conditions, dust in the air, and the height of mountains or other features that might block or redirect light. Weather in the twilight zone would be unlike anything we've experienced. It would likely be the most active weather region on the planet, as hot air from the sunny side would constantly meet cold air from the dark side. This boundary might experience nearly constant storms, winds, and precipitation as the atmosphere tried to balance the extreme temperature differences between day and night sides. The concept of seasons would completely disappear on our stopped Earth. Seasons currently happen because Earth's rotation axis is tilted, causing different parts of the planet to receive varying amounts of sunlight as we orbit the sun. But if Earth stopped spinning while maintaining its orbital motion around the sun, the same hemisphere would always face the sun. The sunny side would remain the sunny side throughout Earth's entire year-long orbit, and the dark side would remain perpetually dark. This would create some interesting regional variations. Parts of the sunny side that are currently in winter would suddenly experience endless summer heat, while regions that are currently in summer would continue to bake. But these wouldn't be familiar summer temperatures. They would be the accumulated heat of endless summers, far hotter than anything we currently experience. Plant and animal life, assuming any survived, would face unprecedented challenges in adapting to these new light conditions. Most life on Earth has evolved with the expectation of day-night cycles. Plants have developed internal clocks that help them regulate growth, reproduction, and metabolism based on daily light changes. Animals have evolved sleep patterns, migration behaviors, and hunting strategies, all built around the rhythm of day and night. On the sunny side, plants might initially flourish with continuous sunlight, but many would eventually struggle with the heat and the inability to complete biological processes that require darkness. On the dark side, photosynthesis would become impossible, and most plant life would eventually die unless it could adapt to survive on stored energy or develop alternative energy sources. The twilight zone might become a refuge for life forms that could adapt to constant, dim lighting. Some plants might evolve to maximize their efficiency in low-light conditions, while animals might develop new behaviors suited to a world where the lighting never changes. And what about the concept of time itself? So much of how we measure and think about time is tied to the cycle of day and night. On a world without that cycle, new ways of marking time would need to emerge. Perhaps people would measure time by temperature changes, weather patterns, or the position of the moon and stars, though even those would behave differently on a non-rotating world. It would be a planet divided not by political boundaries or geographical features, but by light itself. The sunny side, the dark side, and the twilight zone between them would become the new fundamental regions of Earth, each with its own climate, its own challenges, and its own strange beauty. If you thought choosing between the beach and the mountains was difficult, imagine choosing between an oven and a freezer. Our stopped Earth would become a planet of stunning extremes, where the difference between the hottest and coldest places wouldn't be measured in tens of degrees, but potentially in hundreds. The sunny side would accumulate heat like a slow-cooking solar oven, while the dark side would become a frozen wasteland that makes Antarctica look tropical. It would be a world where your choice of a dress would literally determine whether you'd swelter or shiver. Let's start with the sunny side, where the physics of endless heating would create conditions unlike anything in Earth's current climate. Without the nightly cooling period that currently allows our planet to shed excess heat, solar energy would accumulate day after day, week after week. Think of it like leaving a car parked in the sun with the windows up, except the car is half a planet and there's no nightfall to provide relief. Initially, the temperature rise would be manageable. Earth's oceans and atmosphere are remarkably good at absorbing and distributing heat. But even these massive heat sinks have their limits. As water temperatures rose, more and more would evaporate into the atmosphere, creating incredibly humid conditions that would make the heat feel even more oppressive. Eventually, in the regions directly facing the sun, temperatures could climb high enough to boil water, turning rivers into steam and making the very air shimmer with heat. The hottest spots would likely be large, flat areas with little vegetation or water to moderate the temperature. Deserts, which already experience extreme heat during the day, would become furnaces. Rocky plains would become too hot to touch, their surfaces radiating heat like giant stovetops. The air would rise in massive columns, creating thermal updrafts so powerful they might be visible as permanent heat mirages dancing across the landscape. But the heat wouldn't distribute evenly. Mountains on the sunny side would create their own weather patterns, with hot air rushing up their slopes during the endless day. Valleys might become heat traps, collecting the hottest air and creating localized ovens. Coastal areas might fare slightly better, as bodies of water would moderate temperatures somewhat, though even the oceans would gradually warm beyond anything we've experienced. Meanwhile, on the dark side, an entirely different kind of extreme would unfold. Without the sun's warmth, these regions would begin the slow process of radiating their heat out into space. Unlike the sunny side's rapid heating, this cooling would be gradual but relentless. Earth's surface normally loses heat to space every night, but it's replenished by the next day's sunlight. On the permanently dark side, there would be no such replenishment. The cooling would follow the laws of thermal radiation, with temperatures dropping steadily toward the background temperature of space, which is about -270 degrees Celsius. Of course, Earth's atmosphere would slow this process considerably, acting like a blanket that traps some heat. But even with atmospheric insulation, the dark side would eventually become colder than anywhere on current Earth. Water would be the first casualty of this extreme cooling. Oceans on the dark side would begin to freeze, starting at the surface and gradually working deeper. But this wouldn't be ordinary sea ice. Without tides and currents to keep the water moving, and with temperatures continuing to drop, these frozen oceans could become incredibly thick layers of ice, potentially freezing solid to their very depths. The atmosphere itself would begin to behave differently in these extreme temperatures. As air on the dark side cooled, it would become denser and begin to settle. Eventually, if temperatures dropped low enough, gases that normally remain airborne might begin to condense and even freeze. The sky itself could become a strange mix of ice crystals and frozen gases, creating atmospheric phenomena we've never observed. But perhaps the most dramatic climate feature would occur where these two extremes met. Along the boundary between the furnace and the freezer, the temperature gradient would create weather systems of incredible intensity. Hot air from the sunny side would constantly rush toward the cold air of the dark side, creating winds and storms that would make our current weather seem gentle by comparison. This boundary zone would likely experience nearly constant storms, as the atmosphere tried desperately to balance the extreme temperature differences. The hot air would rise and flow toward the cold side at high altitude, while cold air would rush along the surface back toward the hot side. This circulation would create a permanent belt of severe weather around the planet's circumference. These storms wouldn't be like anything we currently experience. They would be driven by temperature differences far greater than those that create our most powerful hurricanes. The winds could be sustained at speeds that would make current hurricane-force winds seem like gentle breezes. Lightning would be almost constant as the turbulent air created massive electrical charges. The twilight zone would experience the most moderate temperatures, but even moderate would be relative. The boundary between extreme heat and extreme cold would create its own challenges. Parts of this zone might experience rapid temperature swings as weather systems moved heat and cold air back and forth. Other areas might settle into more stable conditions, becoming the last refuges of familiar Earth-like temperatures. Humidity would vary dramatically across these regions. The sunny side would eventually become incredibly humid as water evaporated from overheated oceans and rivers. The dark side would become extremely dry as moisture froze out of the air. The twilight zone might experience the strangest weather of all, with hot, humid air from the sunny side meeting cold, dry air from the dark side, creating conditions ripe for constant precipitation. Over time, these extreme conditions would reshape the very landscape. Rocks would expand and contract with temperature changes, creating new patterns of erosion and weathering. The freeze-thaw cycles in the twilight zone could be particularly dramatic, as water repeatedly froze and melted with the shifting weather patterns. It would be a planet where climate isn't just about latitude and altitude, but about your position relative to the sun. A world where the phrase, "it's hot on the sunny side," would take on a whole new meaning, and where the concepts of hot and cold would be redefined by extremes we can barely imagine. Life, as we've learned throughout Earth's tumultuous history, is both remarkably stubborn and surprisingly creative. Our planet has witnessed ice ages, asteroid impacts, massive volcanic eruptions, and dramatic changes in atmospheric composition, yet life has persisted through it all. So while a suddenly stopped Earth would certainly be catastrophic, it's worth wondering, might some life find a way to survive even this cosmic disruption? The answer is both yes and no, depending on where you look and what kind of life we're talking about. Let's start with the most likely survivors, the deep dwellers. Far beneath the ocean surface, in the eternal darkness of the deep sea, life already exists without any dependence on sunlight or Earth's rotation. These creatures live around hydrothermal vents, volcanic springs on the ocean floor that provide heat and chemical energy completely independent of solar cycles. Bacteria and archaea around these vents have evolved to extract energy from hydrogen sulfide and other chemicals, creating ecosystems that could theoretically survive even the most dramatic surface changes. These deep-sea communities might actually be largely unaffected by Earth's stopped rotation. The crushing pressure of miles of water above them would continue to provide stability, and the geothermal energy from Earth's interior would keep flowing regardless of what's happening at the surface. Fish, tube worms, and other creatures adapted to this environment might continue their lives much as before, unaware that the world above had fundamentally changed. Underground life, too, would have a better chance of survival. Bacteria living in deep rock formations, cave ecosystems, and underground water systems exist in relatively stable environments that don't depend on surface conditions. These subsurface biomes might serve as seed banks for life, preserving genetic diversity through the catastrophic changes above. But what about life on the surface? Here's where creativity and adaptation would need to work overtime. In the twilight zone, that band of perpetual dawn circling the planet, conditions might remain just tolerable enough for some life to persist. Plants that could adapt to constant low-light conditions might have a chance. Think of shade-tolerant forest floor plants, but taken to an extreme vegetation that could photosynthesize in permanent twilight conditions. Some existing plants already show promise for this kind of adaptation. Mosses and ferns, which evolved in low-light forest conditions, might be among the first to adapt to twilight zone living. Certain algae and cyanobacteria, already capable of photosynthesis in very dim light, could potentially form the base of new food webs in these regions. Animals in the twilight zone would face different challenges. Without day-night cycles, many behavioral patterns would need to be completely reorganized. Nocturnal animals might actually have an advantage, as they're already adapted to low-light conditions. Owls, bats, and other night hunters could potentially thrive in a world of permanent twilight. Migration patterns would be completely disrupted, but they might also create new opportunities. Instead of seasonal migrations following temperature and food availability, animals might develop new patterns of movement between different temperature zones. Creatures might migrate not north and south with the seasons, but between the hot, temperate, and cold regions of the new climate bands. Some life forms might actually benefit from the new conditions. Cold-adapted organisms, currently restricted to polar regions and high altitudes, might find vast new territories on the dark side of the planet. Antarctic fish, polar bears, and Arctic plants could potentially expand their range dramatically as large portions of the planet became permanently cold. Similarly, heat-loving organisms might flourish on parts of the sunny side, at least initially. Desert plants and animals, extremophile bacteria that thrive in hot springs, and other heat-adapted life forms might find paradise in the warming regions, though even they would eventually face limits as temperatures climbed beyond habitability. Human survival would require tremendous ingenuity and cooperation. Our current civilization depends entirely on predictable day-night cycles, seasonal weather patterns, and stable ocean currents. But humans are remarkably adaptable, and our technology might allow survival in ways impossible for other species. Underground cities might become humanity's best option for long-term survival. Geothermal energy could provide both heat and electricity, while controlled environment agriculture could produce food independent of surface conditions. Some current research stations in Antarctica and submarine crews already demonstrate humans can live in isolated, controlled environments for extended periods. The twilight zone might also support human communities, particularly those that could harness the perpetual storms and weather activity for renewable energy. Wind farms in the boundary zone between hot and cold regions could generate enormous amounts of electricity, while the constant precipitation might support agriculture in carefully designed greenhouses. Technology could help life adapt in ways evolution alone couldn't achieve quickly enough. Genetic engineering might allow crops to grow in constant twilight or extreme temperatures. Artificial ecosystems could preserve species through the transition period, while selective breeding could accelerate natural adaptation to new conditions. Marine life would face mixed prospects. While surface ocean ecosystems would be devastated by the initial catastrophe and subsequent climate changes, the deep ocean might remain relatively stable. Over time, new marine ecosystems might develop in the relocated polar oceans, though they would be quite different from current marine life. Perhaps most importantly, the extreme conditions might drive rapid evolutionary change in surviving populations. When environmental pressure is intense, evolution can work surprisingly quickly. Isolated populations in different climate zones might rapidly develop new adaptations, potentially leading to entirely new species within relatively short timeframes. Symbiotic relationships might become even more important than they are today. Plants and fungi, animals and bacteria, different species working together might have better survival chances than any organism trying to adapt alone. The extreme conditions might favor cooperative survival strategies over competitive ones. The key insight is that while most current ecosystems would collapse, the fundamental ingredients for life, liquid water, chemical energy sources, and basic elements, would still exist in various locations around the planet. Life might retreat to refuges and gradually spread back out as conditions stabilized into new patterns. It would be a smaller, stranger, but potentially still living world, different from anything we know, but possibly still capable of supporting life in forms both familiar and entirely new. After all, life has survived worse catastrophes before, and given enough time, it might just find a way to make even a stopped Earth home. Earth, it seems, was never quite as round as we politely pretended. Our planet is actually what geophysicists call an oblate spheroid, which is a fancy way of saying it's flattened at the poles and bulges at the equator, like a ball that someone sat on very gently. This cosmic love handle exists because Earth spins, and spinning creates centrifugal force that pushes everything outward, especially at the equator where the rotational speed is highest. But if Earth stopped spinning, this ancient bulge would slowly begin to settle, fundamentally changing the shape of our planet. Currently, Earth's equatorial diameter is about 26 miles larger than its polar diameter. That might not sound like much on a planet that's nearly 80 miles wide, but it's enough to affect everything from satellite orbits to the flow of ocean currents. This bulge has been building up for billions of years as Earth's rotation gradually pushed material outward from the center toward the equator. It's carved into the very bedrock, creating a permanent record of our planet's spin. Without rotation, this bulge would become geologically unnecessary. Gravity would begin the slow work of redistributing Earth's mass into a more perfectly spherical shape. But this wouldn't happen quickly. We're talking about moving continents here, and continents are notoriously slow to relocate. The process might take millions of years, but it would be inexorable, like watching a very, very slow-motion water balloon settle into a perfect sphere. The immediate effects would be more subtle, but equally important. Earth's gravitational field, which currently varies slightly due to the planet's oblate shape, would begin to change. The strength of gravity at any given location depends partly on how far you are from Earth's center of mass. Currently, because of the equatorial bulge, people at the equator are actually farther from Earth's center than people at the poles, so they experience slightly weaker gravity. On our stopped Earth, as the bulge gradually settled, gravity at the equator would slowly increase, while gravity at the poles would slightly decrease. This might not seem like much. We're talking about changes measured in fractions of a percent, but it would be enough to affect the orbits of satellites, the accuracy of GPS systems, and even the precise timing of atomic clocks. The redistribution of mass would also affect Earth's moment of inertia, a measure of how the planet's mass is distributed relative to its rotation axis. Currently, having more mass concentrated at the equator makes Earth slightly more stable in its rotation, like a spinning top with most of its weight around the rim. As the bulge settled and mass moved toward the poles, Earth would become easier to tip or wobble if it ever started spinning again. Tidal forces would change too, though in subtle ways. The Moon's gravity pulls on Earth, creating tides in our oceans, but it also causes tiny tides in the solid Earth itself. The planet actually flexes and bulges very slightly as the Moon passes overhead. On a non-rotating Earth, these tidal forces would create different patterns of stress in the planet's crust, potentially affecting earthquake patterns and volcanic activity. The loss of the Coriolis effect would have immediate consequences for anything that moves across Earth's surface. Currently, this invisible force, caused by Earth's rotation, deflects moving objects to the right in the northern hemisphere and to the left in the southern hemisphere. It affects everything from the path of artillery shells to the flow of air in weather systems. Without it, projectiles would fly in perfectly straight lines, weather patterns would lose their characteristic spiraling motion, and even toilet water would drain differently, though not in the dramatic way popular myths suggest. Ocean currents, which currently depend heavily on the Coriolis effect to maintain their circulation patterns, would be forced to reorganize completely. The Gulf Stream, which carries warm water from the tropics toward Europe, exists partly because Earth's rotation deflects the flowing water. Without rotation, entirely new current patterns would emerge, driven purely by temperature differences and wind patterns rather than rotational effects. Even the length of a day would change, though not in the way you might expect. Currently, Earth's rotation is gradually slowing down due to tidal friction with the Moon. This means our days are getting longer by about 1.7 milliseconds per century. But if Earth stopped rotating, the concept of a day based on rotation would become meaningless. Instead, a day might be redefined as the time it takes Earth to complete one orbit around the Sun, what we currently call a year. The planet's magnetic field would face perhaps the most dramatic changes. Earth's magnetosphere, which protects us from harmful solar radiation, is generated by the motion of molten iron in the planet's core. This motion is influenced by Earth's rotation through something called the Coriolis effect in the core's fluid dynamics. Without rotation, the patterns of flow in the molten core would change dramatically, potentially weakening or completely reorganizing our magnetic field. A weakened magnetic field would have serious consequences for any surviving life. More cosmic radiation would reach Earth's surface, potentially making large areas uninhabitable. The aurora, those beautiful lights that dance around the poles, might disappear entirely or appear in completely different patterns. Satellite electronics and any remaining technology would be more vulnerable to solar storms and cosmic radiation. The atmosphere itself would redistribute according to the new gravitational field. Currently, the atmosphere is slightly thicker at the equator due to centrifugal force. Without rotation, atmospheric pressure would become more evenly distributed, with slightly higher pressure at the poles and slightly lower pressure at the equator. Perhaps most remarkably, all these changes would happen according to the same fundamental laws of physics that govern everything from spinning figure skaters to orbiting planets. Conservation of angular momentum, gravitational attraction, fluid dynamics, the same principles that describe a dancer's spin would play out on a planetary scale as Earth adjusted to its new, non-rotating reality. It would be a planet slowly finding its new balance, settling into a shape and behavior pattern unlike anything in its 4.5 billion year history, but still following the elegant mathematical rules that govern motion and matter throughout the universe. Sometimes it takes imagining the end of something to truly appreciate its quiet, everyday miracles. After wandering through the catastrophic consequences of a stopped Earth, we find ourselves with a deeper appreciation for the gentle rotation that carries us through our days and nights. What seemed like empty space and stillness revealed itself to be motion and momentum, a delicate balance of forces that creates the very conditions that make life possible. Our spinning planet isn't just moving through space, it's dancing, and that dance choreographs everything from the winds in the sky to the beating of our hearts. Think about how many things we take for granted that depend on Earth's rotation. The sun rising in the east and setting in the west, the gentle progression of seasons, the predictable patterns of weather that allow farmers to plant crops and sailors to navigate oceans, the Coriolis effect that gives hurricanes their distinctive spiral shape. Even the basic fact that we have distinct days and nights, periods of activity and rest that match the biological rhythm's evolution has built into almost every living thing on Earth. Our rotation doesn't just create these patterns, it maintains them with remarkable consistency. Earth completes one rotation every 23 hours, 56 minutes, and 4 seconds, and has been doing so with only tiny variations for billions of years. This cosmic punctuality has allowed life to evolve internal clocks that match the planet's rhythm. Plants open and close their flowers with the daily cycle. Animals migrate with seasonal patterns. Humans feel most alert during daylight hours and sleepy as night approaches. All of this biological clockwork depends on the reliable rhythm of a spinning world. But our rotation is not eternal. Earth's spin is gradually slowing down, and it has been for its entire history. The culprit is tidal friction from the moon. Just as Earth's gravity creates tides in the moon's rock, yes, the moon has tides too. The moon's gravity creates tidal bulges in Earth's oceans. As our planet rotates, it has to drag these tidal bulges along, and this creates friction that gradually slows our spin. The effect is incredibly small. Our days are getting longer by about 1.7 milliseconds per century. At that rate, it would take about 140 million years for a day to become 25 hours long. But the process is real and measurable. We know this partly from studying ancient coral reefs, which grow in daily patterns like tree rings. Fossil corals from 400 million years ago show that Earth's days were only about 22 hours long back then. This gradual slowing means that in the very distant future, Earth might naturally approach something like the stopped rotation we've been imagining. But gradual is the key word here. Over millions of years, life would have time to adapt to slowly changing day lengths. The sun would rise and set more slowly, seasons would shift gradually, and biological rhythms could evolve to match the new pace. It would be nothing like the sudden stop we've been exploring. There's something poetic about the fact that the moon, which gives us tides and helps stabilize Earth's tilt, is also slowly stealing our spin. It's like a cosmic dance partner that's gradually slowing down the music. And in fact, as Earth's rotation slows, the moon is slowly moving away from us. The energy taken from our rotation is transferred to the moon's orbit, pushing it about 1.5 inches farther away each year. Eventually, billions of years from now, Earth and the moon will be tidally locked, with the same face of Earth always pointing toward the moon, just as the same face of the moon always points toward Earth. But even this future-locked Earth wouldn't be the same as our sudden stop scenario. The planet would still orbit the sun, so there would still be a form of day and night cycle, just one that lasted a month instead of 24 hours. It would be strange and different, but it would happen so slowly that it would seem normal to any life forms around to experience it. Understanding Earth's rotation also helps us appreciate the intricate connections between seemingly unrelated phenomena. The same spin that gives us day and night also helps generate our magnetic field, which protects us from harmful solar radiation. The rotation that creates the Coriolis effect also helps drive the ocean currents that distribute heat around the planet and regulate our climate. The centrifugal force that creates our equatorial bulge also affects the strength of gravity at different latitudes. These connections remind us that Earth isn't just a ball of rock with some water and air stuck to it. It's an integrated system where rotation, magnetic fields, atmospheric circulation, ocean currents, climate, and life itself are all interconnected in ways we're still discovering. Change one element and everything else adjusts in response. Perhaps most remarkably, this entire system emerged from the same swirling disk of dust and gas that formed our solar system 4.6 billion years ago. The angular momentum from that ancient rotation is still with us, still carrying us through our days and nights. Every sunrise is a reminder of our cosmic origins, every sunset a consequence of our planet's spin. We're not just living on Earth, we're riding through space on a piece of the original stellar nursery that created our sun and planets. And so, as we come full circle in our journey, we find ourselves back where we started, sitting quietly on a planet spinning through space at over 10 miles per hour, completely unaware of the motion that makes our existence possible. But now, perhaps, there's a new awareness of the delicate physics that governs our days, the ancient dance that rocks us to sleep each night and wakes us each morning. The ground beneath your feet is not still, it's part of a cosmic clockwork that has been ticking steadily for billions of years, creating the rhythm that life itself has learned to follow. And in that rhythm, there's both science and poetry, both mechanical precision and gentle wonder. And so we return to where we began. You, still traveling through space at over 1,000 miles per hour, still blessed with the gentle rhythm of day following night, still cradled by a planet that spins with such steady reliability that we forget it's moving at all. We've imagined a world standing still and found it both terrifying and oddly beautiful, a planet of extremes, where the familiar rhythms of sunrise and sunset give way to endless noon and eternal midnight, where the very air becomes a hurricane and the seas relocate themselves across continents. But perhaps what's most remarkable is not the chaos that would follow if Earth stopped spinning, but the quiet miracle that it continues to spin at all. Every sunrise, every sunset, every gentle breeze is a gift of angular momentum, a cosmic inheritance from the swirling disk of dust and gas that became our solar system billions of years ago. Tonight, as you drift off to sleep, you're riding on a planet that rotates with such perfect consistency that we build our entire lives around its rhythm. And tomorrow, when you wake, the sun will rise again, not because it's moving, but because we are, spinning quietly through space, carrying our dreams and our tea and our small daily miracles along for the ride. There's something deeply comforting about that constancy, that reliable motion we never feel but always depend on. In a universe full of change and uncertainty, Earth keeps spinning, keeps dancing, keeps rocking us gently through our days and nights. Thanks for joining us here at Sleep Science, where even standing still becomes a journey. Sleep well,